lesson is on the central limit theorem. Before we get started looking at what the central limit theorem states, I want to just take a look at this applet real quick. Okay, so in this applet, we can choose different types of distributions along with different sample sizes. So if we just look at an exponential distribution for a moment, sample size 1, you see that an exponential distribution is very right skewed. But if we increase sample size and we look at the mean of those samples, we see that the shape starts to change. So it's a little less right skewed for that particular sample size. Let's increase that sample size to, let's say, 30. Now when we take the mean of those 30 readings and plot those means, we can see that the distribution looks about normal. All right, let's look at a uniform distribution for a moment. Again, sample size of just 1. Uniform means takes on the same value across the board. So we can see this shape is relatively flat. Let's again go ahead and increase the sample size. And this means that if we take, let's say, 10 samples, find the mean, and plot those means over and over again, oh, look at what happens to the shape. Looks familiar, and as we increase that sample size, it even gets more normally distributed. A normal distribution, of course, for sample size 1 is going to look normal, and it's going to continue to stay normal throughout various sample sizes. I'm trying to stick to a sample size of 30 here, but notice the shape, the variance does decrease. The standard deviation and variance decrease for larger sample sizes. Okay, so this takes us back to what the central limit theorem actually states. It says if you have a population with mean mu and standard deviation sigma and take sufficiently large random samples, sufficiently large in this case means at least 30, from the population with replacement, then the distribution of the sample means will be approximately normally distributed. So it really doesn't matter what the distribution, the initial distribution looks like. When we take a mean of at least 30 readings and look at the distribution of those means, that shape is going to be normal. If we're taking the mean of at least 30 data values, then the new z-score formula is going to state we're going to take the sample mean minus the population mean divided by the standard deviation divided by the square root of the sample size. So this is what I call the central limit theorem z formula. And this is the z formula for if we just have one data point. So we're replacing the data value with the mean of at least 30 data points, and the standard deviation needs to be divided by the square root of that sample size. Here's the first example that we're going to take a look at together. It says, a bottling company uses a filling machine to fill plastic bottles with soda. The contents vary according to a normal distribution with mean 20.2 ounces and a standard deviation of 1.1 ounce. What is the probability that the sample mean of 40 bottles is less than 20 ounces? All right, let's go ahead and draw out this distribution. So it really doesn't matter what the initial distribution looked like. We know because we're sampling more than 30 that the sampling distribution of sample means will be normal. It will be centered at 20.2. The standard deviation is 1.1 for just one bottle. And we're finding what's the probability that the bottles will have less than 20 ounces in them. Okay, so we're going to take that standard deviation and divide it by the square root of the sample size, which is 40, and that's going to give us the standard deviation of the sample means. We're going to need to turn this 20 ounces into a z-score, similar to what we did before. So we're going to take the sample mean of 20 minus the population mean of 20.2 and divide it by the standard deviation of sample means, which is 1.1 over root 40. Let's go ahead and find that z-score. Okay, I went ahead and did that math in the calculator on the right side and rounded that z-score to 2 decimal places. So that's negative 1.15. Now we're going to go ahead and look this up on the negative distribution. Negative 1.15 is corresponding to a probability of 0.1251. In other words, 12.51% of all sample means of 40 will be less than 20 ounces of soda. Okay, example 2. The length of a pregnancy varies according to a normal distribution with mean 264 days and a standard deviation of 16 days. Select a sample of 30 pregnant women. What is the probability that the mean length is greater than 270 days? All right, let's draw out this distribution. Again, it really doesn't matter what the initial distribution was because we are selecting a sample that is 30 or more. So we know that the distribution of sample means is going to be normally distributed with mean 264. The standard deviation of just one pregnancy is 16 days. So if we want the standard deviation of sample means, we're going to have to divide that by the sample size, which is 30. We want to find the probability that the sample mean pregnancy is going to last 270 days or more. All right, let's convert that data value, that sample mean rather, into a z-score. So 270 is the sample mean minus the population mean of 264. And we're dividing that by the standard deviation of sample means, 16 divided by the square root of 30. That standard deviation of sample means is also referred to as the standard error. All right, let's go ahead and find that z-value. Okay, I got a z-score of 2.05 if I round that to 2 decimal places. Let's look that up on the positive z chart. 2.05 corresponds to a probability of 0.9798. 0.9798. Now that is the probability from this line to the left. So I'm going to have to use complement rule to find this right shaded region. So I'm going to take 1 minus that probability to get the probability that we want. Oops, 9798. So if I do that over here on my calculator, 1 minus the probability of 0.9798 gives me a probability of 0.0202. So we see that that probability is very, very tiny. Only about 2% of mean lengths of pregnancies will be 270 days or more. Again, that sample size is 30. So we're talking about a mean of 30 pregnancies lasting that long. Okay, this concludes the lesson for today.